Hey you guys. Well, I'm starting at the wrong point here, so I get a little preview of everything. But what we're working on right now is higher order derivatives. Sounds interesting, maybe sounds sophisticated. It really means taking the derivative multiple times, one after the other. So the first thing I have here is a simple quadratic equation, and you would take the first derivative to get 6x plus 2 like you might expect. But if I take the derivative of the derivative and get the second derivative, now note we use this little second, this is called prime notation, so the y prime was first derivative, y double prime is second derivative, and we get 6 for the second derivative. We could even do the third derivative. Watch this. Third derivative would be 0, because you take the derivative of a constant and get 0, and then you'd be done. The farthest you can go with, well, these are polynomials like this one, is you can take the derivative till you get 0. Some functions, when you take the derivative, it just happens, keeps going and going and going, but the idea is a first derivative we know is the rate of change of y, so if it were cost, it would be the rate of change of cost with respect to x, or it would be the rate of change of revenue with respect to time or dollars or things like that. Things we've been doing all along, that's the first derivative. Well, if you take the derivative of the derivative, what you actually get is the rate of change of that derivative function. So in this case, the rate of change of y prime. So it tells you how fast the derivative is changing, which is kind of interesting. Because if anything's changing, the derivative is not constant, it's changing, then you can see how fast it's changing. And then, well, guess what y triple prime is? Derivative of y double prime, or the second derivative. The third derivative is the derivative of the second derivative, and so on. So this just gives you an idea of some notation, some terminology. A derivative is the rate of change of the function of which you took the derivative. So here's a graph. Now, I've done this one years and years. I've told you guys a little bit. If I take a trip, it used to be from Minneapolis, I'd always talk about my trips to Des Moines, exotic trips to Des Moines. And now, let's say we're distance from Drake, so wherever it is you happen to be heading. Oh, by the way, that's Graham in the background, the little guy with, well, he's got all kinds of stuff. We thought pneumonia and some other things. Anyway, thankfully, Blank Hospital took a little test and told us it was a pretty nasty cold, which is great. So, good news after he had that RSV bout. Anyway, back on track. Here's a little graph of, distance from Drake. Let's say you're heading on a trip. The bend in here, let me highlight a few places. You come to a stop right about here somewhere, maybe a rest stop. This downhill piece of a negative distance over time means I must be going backwards until I stop again and then head on my way on a particular trip. Well, all that is good fun, but if you want to look at how fast you're traveling, we all know that you want to look at, rates of change, the slope of the tangent line. And if I put numbers in there and made some up, it'd be 5, let's say, and -2 at the second one, 7 at that. That'd be our first derivative. Rate of change, slope of the tangent line. Don't ever forget that. That's the most important thing. But if you want to really look at those, a whole bunch of them, here's a couple more. When you get to the peak there, wherever the slope of the tangent equals 0, it seems to be at a peak or at a valley when things kind of get to a point. It teeters at the top there. There's Graham. But if I actually make a graph of the values of the derivative, this is what it would look like. All the derivative values, if I did slopes of tangent lines on every little spot, it would look something like that purple graph there. So you can actually graph the first derivative itself, which is the idea of if you take the derivative of a function, and that itself, the derivative itself is some equation, some function, you could graph both at the same time. Crazy, huh? So what I have is I wanted to show you, here's a graph of y and here's a graph of y prime. So just a little bit more clarity. If you notice 5, the height I marked there on the graph, that corresponds to when the slope of that tangent line was 5. And then notice when the graph goes to -2 slope, the derivative graph, the purple one, hits a height of -2. So the derivative graph is just plotting all the slope of the tangent line values along the way. When my derivative is, slope of the tangent line is 0, notice the purple derivative graph is at a height of 0. So I notated that with little markings. So the graph really is just what the value of all the slope of the tangent lines are. And then, well, I can get into more detail on that another day, but that was just a little preview of what it could look like. Now, here's another, let's just talk about higher order derivatives, first, second, third, and so on. If I just take the first derivative of this function, and I get 6, and then the second derivative would be 0. there's a question you might get in the homework, well, it's already posted, and say, hey, find the second derivative of this function. That means take the derivative twice, tell me what you get, move on. Here's a second idea. Here's another function, another quadratic. Find the second derivative of this. That means take the derivative twice. Once gives you 18x plus 2. A second time gives you just 18. So it's same derivative rules. These are all just power rules, nothing fancy. Of course, you know derivatives can get more complicated. So here's a third option. If I give you this 3 times x squared plus 3x to the third, chain rule. So you get a derivative of the outside with the inside untouched times the derivative of the inside. So watch carefully. So there's the chain rule. Got to be careful. I went ahead and did the first derivative. Okay, derivative of the outside, so 3 times 3 is 9. Left the inside the way it is. Now it's to the second power. Then right to the right there, you want to look, there's this derivative of the inside, really important. Okay, keep going. Now what about the second derivative? Well, you know that 9 that's out in front of there? I'm going to actually ignore that 9 for a minute. You can actually ignore that and put it back in when we're done. So let's imagine it's not there for a second. Okay, so I'm going to take that out. And then let's just take the derivative of the pieces that I have. Now, this is the derivative of the first times the second unchanged. Let me kind of give you an idea where those come into play. The derivative of the first is that kind of function on the left. Let's color code it here. See the first function in yellow? That's the first one, derivative of the outside with the inside untouched times the derivative of the inside, little chain rule. And then the second function in green, circled in green and then notated in green there, untouched, 2x plus 3. Plus the derivative of the second times the first unchanged. Let's color code it again. First times d second. So there we are. That was a product rule because of two functions being multiplied together. Did you know a product rule can have a chain rule in it? So when you're doing the derivative of the first, you have to go through that whole process there. So that circled yellow function, if that's my first function, derivative of the first is a chain rule. Second untouched, the green, 2x plus 3. Derivative of the second is just 2. Did I write that right? Oh, I wrote those backwards. Hey, can I fix that real fast? Just put my arrows in the wrong place in my notations. Did you see that? Derivative of the second, well, that had to be confusing, is the first one on there, and then the first function untouched is that one over there. Sorry about that. Talk about turned around. So we'll just maybe just erase those all together. I can make this better. We can call this first, and then this one here d second. Did you see that right away? Were you noticing that? Oh man, I was distracted by this super cute baby over here making all kinds of crazy noises. Alright, moving on. So basically the only thing is now is remember that 9 I took out? Got to put it back. So if I put it back, I just take 9 times this big old derivative that I have. I didn't write it in the values, so I'm just kind of showing you the spaces where they would be, but you just put in 9 times what you have. Thanks, Grant. So that's 9 times 2, which would be 18. So let's keep an eye out for when you do this product rule with chain rule inside it. By the way, this is just getting the first derivative we got with the chain rule. Then I took a second derivative which required the product rule because the two functions multiplied. So you can see how quickly derivatives can get pretty complicated pretty fast just because you have to do multiple rules on top of each other. Just go one at a time. Just kind of keep your eye on what rule you're working with. Do one piece, one derivative at a time. You'll be good. Number 4. Let's see, how about this? Find f triple prime of 1/2. That means I want to go get the third derivative, stick 1/2 in. So here's a derivative. Wait, I'm not even going to take the derivative yet. I got to actually take and pause this. Wait, let's go a little bit further. Okay, so what I've got here is I rewrote the function. Instead of square root, 1/2 power. Then I did a little chain rule. Now this is the derivative of the outside you see right now. See? Derivative of the outside. Now we need the derivative of the inside, which is just 2. Okay. Now we're going to do the derivative again, but before I do that I want to simplify a little bit. So I always simplify a little if I can. So I simplified in the beginning, made it 1/2 power. Now I'm going to simplify a little bit by canceling some. 2 times 1/2 is just 1. Now let's take the derivative again, f double prime. Here it comes, negative 1/2 because I take the power out front, reduce it by 1, keep the inside untouched, see, untouched inside right there, times the derivative of the inside, which is 2 again. And then we can do some canceling. 1/2 times 2, don't forget the negative is just, those cancel to 1. Third derivative, here it is, negative 3/2 times the negative that was already out there, so watch out. Remember there's a negative here and a negative here, so together they made a positive outside here. Let me clear that up a little bit. It's kind of messy. Okay, the 3/2 up front, inside untouched again. If I take away 1 from negative 3/2, the reason I got that is I subtracted 2 over 2. And that makes negative 5/2. Okay, and then times the derivative of the inside again. And like you'd expect, I'm going to simplify a little bit. You know, those divided by 2 times 2's I can cancel. This is just 3 times 2 times. Now I put in the 1/2 power in there instead of t. Or, I'm sorry, not 1/2 power, 1/2 for t. And so this thing reads now 3 on the outside times 2 times 1/2 plus 3, all to the negative 5/2 power. Definitely a calculator problem. Negative 5/2 power, you can do the caret symbol and then make sure you put 5 over 2 in parentheses, negative 5 over 2. Or just be careful, make it negative 2.5, whatever works. And you should get 0.09375. So those are just multiple derivatives, putting a value in this case, and then actually that means you're going to get a number when you're done. And I think that's the end of the road for that's higher order derivatives, and it's about as intense as it'll get, but that's a lot, so be careful. Email with questions. I'll send implicit differentiation a little bit later.